Can you hear me, guys? Can you hear me, everyone? Can you hear me, all of you? Tell me, guys, in the chat box, please. Am I audible? Can you hear me, guys? Can you hear me, everyone? Can you hear me, all of you? Tell me, guys, in the chat box, please. Am I audible? Can you hear me, guys? Can you hear me, everyone? Can you hear me, all of you? Tell me, guys, in the chat box, please. Yes, sir, audible. Mukul Manpuri, yes, sir, we can hear you. Okay, no problem. Can you hear me, guys? Can you hear me, everyone? Can you hear me, all of you? Tell me, guys, in the chat box, please. Good. Now see. Yes, sir, audible. Mukul Manpuri, yes, sir, audible, everyone. Okay, no problem. Can you hear me, guys? This is the conservation of volume which I am talking. Can you hear me, everyone? A initial by A final, D initial by D final is equals to L final by L initial. Now, can you hear me, all of you? Tell me, guys, in the chat box, please. Now, guys, if we have these kind of results, good. Now see. Yes, sir, audible. Mukul Manpuri, yes, sir, audible. Everyone, okay, no problem. Can you hear me? So if guys, the L final by L initial is 1 plus can you hear me, everyone? We can also write by A final, D initial by D final, write like this. L final by L initial. This is a very important formula. 1 plus. Now, can you hear me, all of you? Tell me, guys, in the chat. D initial by D final. Right, square. I hope this is perfect. Clear? This is very, very important result. Okay, 1 plus E L final by L initial is equals to A initial by A final by D final the whole square. Right. Now, guys, let's understand. I hope this is perfect. This is the result. Clear? This is very, very now important. Now, everyone see. If I am talking about the true strain. Okay, if I am talking about the true strain, A initial is equals to A initial by A final by D final the whole square. Right. Now, guys, let's understand. True strain is denoted as epsilon. I hope this is perfect. This is the result. True strain is denoted as epsilon. Right. Very now, everyone see. Epsilon. If I am talking about the true strain. True strain is actually. Okay, if I am talking about the true strain, change to A initial by A instantaneous length upon final instantaneous. Right. Now, guys, let's understand. Strain is denoted as epsilon. Change in I'm not. I hope this is perfect. This is the result. True strain is denoted as epsilon. Right. Very now, everyone means DL epsilon by L. If I am talking about the instantaneous change in length upon instantaneous length, right? DL by L. Okay, if I am talking about the true strain, change if I just want to calculate the total true strain, my dear. So we need to integrate. Now, guys, let's understand. Is denoted as epsilon. Change in I'm not. I hope this is perfect. This is the result. DL by L. Epsilon, right? Very now, everyone means DL epsilon by L. If I am talking about the instantaneous change in length upon instantaneous length, right? DL by L. This is your instantaneous. This is your true. Okay. Now. Now guys, see, this you can write d epsilon, right? Because it is instantaneous to strain. So this is the main formula of the true strain. Once you integrate both the sides, you are going to get this. Right, this is the formula of true strain. Now one by one, let's understand. If I am going to integrate this, what we have, the first formula, that is ln L, and integrate from both the sides, L initial to L final. We have ln L final by L initial. Now you know very well, I'm writing all the formulas, my dear, for your better understanding. This is very, very important. See, first formula of the true strain is ln L final by L initial. You know very well L final by L initial is L final by L initial. We have, that is your area initial by area final. Area initial by area final. You can write ln area initial by area final. This is going to be your 2 ln diameter initial by diameter final. It is what? It is your d initial by d final ka whole square, and whole square comes into the first place of the log. You know basic rules of the logarithm. And one another formula, L final by L initial is your 1 plus E. Means true strain is ln 1 plus E. True strain, whenever length is given, you can use the first formula to calculate true strain. When your area is given, second formula, diameter is given, third formula, and engineering strain is given, then fourth formula, right? And basic formula, if L is the variable, so then you can integrate dl by L, L initial to L final. These are the basic terms. Remember that. Clear? Clear. This is the true strain. Now, next is your true stress. True stress is your sigma T. True stress is, my dear, it is actually the ratio of it is the load by instantaneous area. Load by instantaneous area. Load by instantaneous area. Now see, load is your what? Load by instantaneous area. Load is your P, and area at any particular instant, P by A. Right? A is your instantaneous area at any particular instant. Suppose at t is equals to 5 seconds, you see the deformation. Because whenever you apply the load, area is getting decreased. At a particular instant, what is the area that we use, right? Now there is one formula that we derive. What we do in the mathematics, see, true stress is equals to P by area. P by what? P by everyone. This is suppose I am going to multiply by A naught into A naught by A. This you can call, so we can call it like P by A naught is what? P by A naught is your sigma naught. Sigma naught. And your A naught by A, sorry, this is your A. A naught by A, what we call A naught by A. That's quite simple. First, just let me write. See, if we apply the conservation of volume, we know volume is conserved. So initial volume V naught is equals to the volume at any particular instant, because initially area is A naught, length is L naught. But once you apply certain load, the length is going to increase and the diameter is getting decreased. So there, the volume remains constant. So volume is constant. So you can write A naught L naught, and at any instant, that is A into L. So we can write A naught by A as L by L naught. What we can write, my dear? L by L naught. Okay. So here A naught by A, L by L naught means instantaneous length upon initial length. So you know this ratio is called what? You can see. We have the ratio area, initial area by final area. So you can write initial area by instantaneous area, final instantaneous length upon initial length. So it will be 1 plus engineering strain. Engineering strain at instantaneous point. So 1 plus E we can equate with this, right? So LF by, so we can equate it as a 1 plus E. So therefore, we have this result, that is a true stress is equals to P by A. P by A naught is your nothing but engineering stress into A naught by A, and true stress is equals to sigma naught into 1 plus E. Clear? Sigma naught into 1 plus E. Sigma naught into 1 plus E. So these are the formula which you need to remember. That is a true strain formula, true stress formula, ln1 plus E, here sigma naught 1 plus E, and sigma naught is your P by A naught. These are the all formula. Note down, everyone. Volume constant VFC. So I'm giving you time to note down this. Please have a look and note down. I'm giving you time. Sir, audio is on loop. Coordinator, please check the audios. Done, everyone? Give me tell me that you have noted down the first slide, then I'll show you the second slide, then third, and then fourth. Clear, everyone? Note down this part. Done, guys. Good. Shall we proceed now? Once done, please tell me. Done. Very good. Guys, next discussion. See everyone. One more thing which I want to highlight. See, See, there is a law that is called your strain hardening law. See, now you have the results. If I am drawing the graph, sigma and strain, right? That is true strain versus true stress versus true strain. So true stress versus true strain graph is always increasing. Remember that, like this. There is no upper yield and lower yield. It is always throughout increasing. Okay. Now, guys, this is the Hooke's law. It follows the Hooke's law, my dear. Here, right? It follows the Hooke's law here. Elastic region follow the Hooke's law, right? Elastic region. This is the elastic region. It follow the Hooke's law. And this is your, my dear. This is your plastic region. It follow a strain hardening law, Power's law of strain hardening. Follow Power's law of strain hardening. Power's law of strain hardening. What is this law, my dear? Let's understand. The law is, you can see, the law states that sigma is equals to k epsilon to the power n, where sigma is equals to true stress, epsilon is equals to true strain, k is equals to strain hardening exponent coefficient, strain hardening coefficient, and n is equals to strain hardening exponent. Strain hardening exponent, right? So here, guys, the unit of true stress is your megapascal, and the unit of K is also your megapascal. Clear, all of you? Strain having true strain having no units. True strain. Now, guys, I'm showing you some graphs. Here you can see if I'm showing you one graph like this, and if you are drawing a line like this, right? Horizontal line means there is no strain hardening in this. The value of small n is 0. But here in this case, strain hardening, suppose it is like this and it is going to increase like this. It is going to increase. So here the value of n, Power's law, n is equals to 0. Then sigma is equals to k. Therefore, the value is actually at this point is equals to k because n is 0. Always remember when in the plastic deformation region, horizontal line you see n0 and here n is your greater than 0. The value of n actually lies between 0 to 1. 0 to 1. And I'm showing you one more example. If suppose the graph is like this, one graph is this, another graph is slightly increasing like this, another graph is more increasing like this. So here, here n is equals to 0, here suppose n is equals to 0.2, here n is equals to 0.3. The more slow, the more strain hardening, right? Remember that. So guys, this is the one problem which is asked in GATE 2020. For a perfectly elastic material, what is the value of strain hardening? For a perfectly plastic material. For a perfectly plastic material, what is the value of a small n? Tell me in the chat box, everyone. Mukul Manpure, Ansar, Naveen. For a perfectly plastic material, what is the value of strain hardening exponent? N. This is your n is equals to 0. N is equals to, and for perfectly plastic material with strain hardening, n is equals to greater than 0. Right, remember these results. Now one more point, remember that at UTS, ultimate tensile point, it is also called at maximum load, when the load is maximum, because at ultimate point load is maximum, right? And also you can call it as a at maximum load at UTS, and at necking, because necking starts from UTS, right? Necking starts from UTS. Clear? So at maximum load, at the ultimate point, and sometimes at ultimate point. Ultimate point. Whenever these all 4 points is written, at maximum load, at UTS, at necking, remember at this point I'm not going to into derivation, that the true strain is equals to a small n. At this point, the true strain is equals to a strain hardening exponent. True strain is equals to a strain hardening exponent. Remember that. True strain is equals to a strain hardening exponent. True strain is strain hardening exponent. Good. Now please note down, everyone. True strain is equals to, this is important result. Note down. Now, clear, everyone? Are you done with this, or any doubt? Done, everyone? Still not getting confirmation from any of you, so that we can see the problems now. Clear, everyone? Have you note down, all of you? 'Clear now? Now, first problem. '58. See the first problem. The engineer the in, sample is 0.1%. Find out, everyone. Find out, everyone. Do it, everyone. Anyone tell me the right answer? Anyone? Very good, very good. Quite easy problem. See, what is given engineering strain? 1%. It is 0.001, right? So true strain we know very well, that is ln1 plus e. ln1 plus, right? What we are getting, everyone? This we are getting 9 point minus 4. But in percentage, if I am going to convert it, divided into multiply by 100, this is your 0.0999. Right answer is your C. Next question, guys. 59 number question. The true stress, the truest ever true strain curve is given by right? This is the true stress versus true strain curve given. Calculate the true stress. Find out everyone. At maximum load. Everyone tell me fast, what is the right answer for this problem? What is the right answer? Everyone tell me. Quite simple. We know very well. Power's law is given to us. Sigma is equals to 1400 epsilon to the power 0.33. So if you compare it with your main equation, therefore you can say that n is equals to 0.33. At maximum load, we know what true strain is equals to a small n. Means true strain is equals to 0.33, and true strain is what? True strain we got 0.33 at maximum load. So now we need to find out the true stress. So you can use the formula 1400 0.33 to the power 0.33. Sigma is equals to this, we are getting 971 megapascal. Clear everyone? Clear or not? Tell me final answer. This is the true stress at maximum load. Because I have taught you already at maximum load. What I have taught you? See, at maximum load, true strain N is equal. Note down all of you. Clear, shall we proceed to the next problem, everyone? Shall we proceed to the next problem, all of you? Mukul Manpure, is that clear? $1,400 is wrong, Mukul. 1,400 is wrong. Next problem, see. The true stress relationship for a metal is given by sigma is equals to 0.4. The cross sectional area at the start of the test is 100 mm square. The cross sectional area at the time of making is dash mm square. Try, everyone. Find out, everyone. Anyone? Mukul, tell me the answer, Mukul. Still not getting the right answer. Very easy problem. Mukul, what you are doing? Ansar, what you are doing? Guys, today you guys are not solving the problems. Why? What happened? Today you guys are not solving the problem. What happened? Now, guys, I am going to solve this quite easy problem. See. Shall I solve everyone? Shall I solve everyone? 67. See everyone, what is given? The cross-sectional area at the start of the test. Start of the test means A naught is given to us. This is your other students are not participating today. That's very disappointing. Right. This is given to us. And at the time of making, they ask us to find out the area. That's quite simple. See, at the time of necking, I have told you, see, at necking, when the necking begins, true strain is equals to N. So here in this problem, N is your 0.4. N is your 0.4 means true strain is also your 0.4. The true strain is Ln area initial means A naught, final area at the necking, necking is the final area, is equals to 0.4. Means A naught by An is equals to e to the power 0.4. E to the power 0.4 is what? E to the power e to the power 0.4, we are getting this 1.49, right? So here An is your A naught by something, A naught is your 100, 100 by 1.49 means 1.5. So approximately what we are getting everyone, 67.03. Is that clear? Is this clear, everyone? That is the cross-sectional area at the time of decay. I hope this is perfect. Shall we proceed to the next problem? Mukul, shall we proceed to the next problem? Mukul Manpure. Ansar. See, the ultimate tensile strength of a material is 400 megapascal. And elongation up to maximum load is up to maximum load is 35%. The material obey Power's law of stone hardening. The material obey Power's law of true stress, true strain relation. In the plastic right, then the correct true stress true strain relation. Epsilon 0.30. This is the right answer, everyone. Do it. In this problem, guys, this is a very unique problem. In this problem, you need to find out the K and N. Which one is the correct true stress versus true strain relation? Earlier, we have seen 2-3 problems in which the true stress true strain relation were already given. right? Like in problem number 59 as well as in 60. But in this problem, some informations are given. On the basis of that information, you need to find out which one is the correct true stress true strain relation. Means find out the K and N. Do it. Everyone try this. Do it, Mukul Manpure. Option A. Other students. Naveen, where is Naveen? Wrong answer, Mukul. Your answer is wrong. Your answer is wrong, Mukul. Wrong answer. Where is the answer? Sir, option C. Now you have rectified your answer. Absolutely right answer. Absolutely right. Say, my dear. This is a very beautiful problem which I want to highlight in this. What are the values given? The ultimate tensile strength of the material is 400 megapascal. Ultimate tensile strength means sigma naught is given. Tensile ultimate means at UTS the value is given. The values are given at UTS. Sigma naught is, that is 400. And engineering strain is 35%, that is 0.35. Now guys, the material obey the Power's law of strain hardening. So we can at UTS we can find out the other values like ln1 plus E, that is the true strain at this point. ln1 plus 0.35, ln 1.35, ln 1.35. So true strain we are getting 0.30, correct? This is your true strain, my dear. Now calculate the true stress. True stress. True stress is your sigma naught into 1 plus E. 400 into 1 plus 0.35. This we are getting 540. Now some students are getting confused. Once they are getting the value true stress 540 and 0.3, they just tick the answer A. But in the problem, they don't ask you true stress and true stress and true strain. They ask you to find out the K and N. To get this value, we will use the Power's law here. Power's law we know, that is your sigma is equals to k epsilon to the power n. And since we are using at UTS, right? At UTS we are doing, we know very well that at UTS your true strain value, your n is your equals to true strain, means n is equals to 0.30. You can also eliminate some options. N is 0.30 means the option B and option D are wrong, because here the value of n is 0.33, 0.33. This is wrong. Either A or C is the right answer. Now, so now when we put the value, because at UTS we know true stress is your 540, K 0.3 to the power 0. What is the value of K we are getting, all of you? 775, approximately 774.92, means we are getting K as 775. Means the final equation is sigma is equals to 775 epsilon to the power 0.30. Correct, everyone? Is that okay, guys? Is that okay, guys? Clear, everyone? Good. Guys, that's great. Very less students are there today. Only one student is participating. Very less student participating. Guys, I am going to end the today's session now. I'll see you on Monday. 3, 4 more days are required to finish the session, right? Because no one is watching today, so interaction is not good. Only Mukul is there and other students are not there. So it's very disappointing. Okay. Thank you.